Okay, so get this. A fiber optic cable, the type that brings us the internet, is being used to listen to glaciers cracking in Switzerland.
Uh-huh.
Not for sending emails, but for picking up icequakes. It sounds pretty wild, doesn't it?
It really is fascinating. Yeah, we've been digging into some research that was presented at the Seismological Society of America's meeting.
Okay.
And it details how these everyday communication cables are giving us a whole new angle on monitoring glacier seismicity, specifically how crevasses open up.
Right, crevasses, those huge cracks. Now, normally we just think of them as dangerous obstacles. Yeah.
True, they are dangerous.
But you're saying they're actually telling us something important about the glacier itself, like its health.
Exactly. Crevasses are fundamental. They're not just cracks. They really influence how a glacier behaves.
How so?
Well, they can act like channels, Meltwater gets down through them, right to the base of the glacier.
Oh, okay.
And that water can sort of lubricate things between the ice and the rock underneath.
Like oil in an engine?
Kind of, yeah. And that lubrication can actually make the glacier flow faster.
Which means more melting.
Leads to faster flow, potentially more melting, and that ultimately feeds into sea level rise. So yeah, understanding crevasses is actually pretty crucial for the bigger picture.
Makes sense. But I imagine putting traditional seismometers all over a glacier that's full of cracks must be, incredibly hard and risky.
Oh, absolutely. Huge logistical challenges, major safety issues. It's an extreme environment. Conventional methods are just really difficult there.
Right.
And that's where this fiber optic approach is so interesting. You potentially have a system that's already there, or at least easier to deploy, giving us this kind of data.
Okay, so let's get into that.
Yeah.
Using internet cables as earthquake detectors, basically. How on earth does that work?
It's a really clever repurposing, isn't it? So they installed a fiber optic cable on Gornergletscher.
That's the big one in Switzerland.
Yeah, the second largest one there. And this cable, it actually picked up the tiny, tiny vibrations in the ice from crevasses forming nearby.
So instead of light pulses carrying data.
Exactly. The cable itself becomes the sensor. It registers these really small ground movements all along its length. It's quite amazing, really.
And these icequakes from the crevasses opening, are they like the earthquakes we feel from tectonic plates shifting, or something different?
That's a really good question. According to Tom Hudson, one of the researchers involved, they're quite different. He calls them crack sources.
Crack sources.
Yeah, picture it like a pure opening, a fracture just pulling apart in one direction. It's very localized.
Okay.
Which is fundamentally different from tectonic earthquakes, right? Those involve huge shear forces, plates grinding past each other.
Right, massive energy release.
Exactly. And it's also different from, say, an explosion, which radiates energy out in all directions. This is more like a splitting.
So the ice is sort of gently being pulled apart, and that makes these little seismic signals.
In essence, yeah. And what was really neat about this study was that a lot of these crevasse quakes happened super close to the cable, like within 10 meters.
Wow, that close.
Yeah, and that proximity meant they could capture just incredible detail about what was happening during those events.
Okay, but getting this, delicate-sounding cable to actually hear the ice cracking, you can't just toss it on top, can you? It needs to be connected somehow.
You're absolutely right. You need good coupling, as seismologists call it. The cable has to be in really good, solid contact with the ice to sense those tiny movements accurately.
Like pressing a stethoscope properly.
Exactly like that. And on the Gornergletscher, they actually got a bit lucky with their timing. They put the cable down in this sort of shoulder season between summer and winter.
Ah, so no snow cover hiding crevasses. Smart.
Very smart, yes. Avoided that danger. But also a natural process helped them out with the coupling.
Ooh, what happened?
Well, the fiber optic cable is dark, right? So it absorbs more sunlight than the white ice around it.
Okay.
So during the day, it would melt itself just a tiny bit into the ice, and then overnight it would refreeze.
Seriously, it dug itself in.
Effectively, yeah. This daily melt-freeze cycle embedded the cable right into the surface ice. Hudson actually said it was probably the best coupling you could hope for.
Wow. Nature doing the hard work. So, okay, they've got this perfectly coupled listening cable. What did they hear? What did the data look like?
The results were pretty stunning. Just this one cable detected and located, get this, 951 icequakes.
951 from one cable.
Yep. And the seismic signals, the waveforms, they had these really strong oscillations after the main surface waves passed, like an echo almost. It's called a coda.
Oscillations, like a ringing sound.
Sort of. Initially, they thought, maybe there's water sloshing around in the crevasses causing some kind of resonance.
Like whistling wind in a canyon?
Something like that, yeah. But when they analyzed it more closely, they figured that wasn't the most likely explanation.
So what was it then?
They think it's more likely that the seismic waves themselves were bouncing around, reflecting back and forth between all the different fractures in that whole crevasse field.
So the network of cracks itself was creating the echo effect.
That seems to be the stronger hypothesis, like sound reverberating in a complex room, but with seismic waves in the ice.
That paints a really cool picture. And compared to traditional sensors, how much more info did they get?
It was a huge difference. The fiber optic cable gave them nearly 20 times the amount of data you'd get from a typical array of separate seismic nodes.
20 times.
Yeah. Now, obviously, processing that fire hose of data is its own challenge, but...
But you see so much more.
Exactly. You get the complete wave field, essentially. A much richer, more continuous picture of what's happening inside the glacier. It's like upgrading from a few photos to, like, a full movie.
That's a massive leap. And it wasn't just more data, right? They could pick up different kinds of signals, too.
Correct. Fiber optics are sensitive across a really wide range of frequencies. That includes these very slow, low-frequency signals, things that might last for hours or even days.
What do those tell you?
They can show how the ice itself is subtly flexing or deforming over longer time scales, things that traditional seismometers focused on faster vibrations might miss entirely. It gives insight into the glacier's slower dynamics.
Okay, so this is clearly a game changer for studying glaciers. But the researchers hinted it could be useful elsewhere, too, beyond ice.
Absolutely. That's one of the really exciting parts. This success on the glacier strongly suggests this technique could be incredibly valuable for monitoring cracks and stresses in other places underground.
Like where?
Well, Hudson specifically pointed to things like carbon storage reservoirs.
Where they pump CO2 underground.
Exactly. And also geothermal energy systems.
How does listening to ice translate to, say, making sure stored CO2 doesn't leak?
Well, the basic physics is similar, isn't it? You're listening for fractures starting or growing in the subsurface. For carbon storage, you really want to know if any new cracks are forming that could let the CO2 escape. Detecting tiny signals early could be critical.
Okay, I see that.
And for geothermal, understanding the network of fractures, how they change when you inject or extract fluids, that's key to making the system work efficiently and safely.
So it's like the glacier is a giant, relatively simple lab to perfect the technique.
That's a great way to put it. Hudson made that point too. Ice is seismically simpler than rock in many ways. Its properties are better known.
Easier to interpret the signals.
Right. So you can really focus on understanding the source, the physics of the cracking itself in this simpler setting. Then you can take those lessons and apply them to more complex geology, like in a rock formation for carbon storage.
Makes total sense. Learn to walk before you run. So what's next for this research? Where do they go from here?
Well, Hudson mentioned a couple of key goals. One is to use the fiber optics to build up a detailed 3D picture of the glacier's insides.
Like a CT scan for a glacier.
Kind of, yeah. Mapping out its internal structure, variations in how fast seismic waves travel through different parts of the ice. And the other big goal is to really quantify the fractures. Figure out, how dense the fracture network is, how big the cracks are, and pinpoint exactly where these icequakes are originating.
Really zoom in on the cracking process.
Precisely. Understanding the fracture extent and density is a key next step, according to Hudson.
So we're talking about getting this incredibly detailed internal view of how glaciers work, how they fracture and move, all thanks to repurposed internet cables.
That sums it up really well. It's just a fantastic example of taking existing tech and finding a completely new, really powerful scientific use for it.
So wrapping this up, the big takeaway seems to be that these fiber optic cables are, well, a revolutionary tool.
Yeah.
They let us listen in on glaciers in a way we couldn't before, giving us vital clues about their stability, about sea level rise.
Crucial insights.
And beyond that, there's this huge potential to use the same idea to monitor other critical underground systems. It's really quite exciting.
It really is a powerful demonstration of ingenuity, finding new ways to understand our planet using the tools we already have.
Yeah, it really makes you wonder, doesn't it? If technology designed for one thing, like communication, can suddenly become our ears to listen to the Earth, what other existing technologies might be out there just waiting for us to find a completely unexpected way to unlock more secrets about our world, or even beyond?